recently I had a long time when I was waiting for an appointment, and to pass the time, I started thinking about the Luca numbers. These are a set of numbers which crop up all over the place in mathematics, and I was thinking in particular what happens if we treat the Luca numbers as a continuous rather than a discrete set, and particularly how would they look if you plotted them in the complex plane. So the results were quite interesting, and I wanted to share them, so that's why I'm making this video. To introduce what they are, I'm going to start with a probably more familiar set of numbers, the Fibonacci numbers. So these start with 0 as the 0th Fibonacci number, then the first number is 1, and then all subsequent numbers are sums of the preceding two terms. For example, the second Fibonacci number will be 0 plus 1 is 1, the next one will be 1 plus 1 is 2, and so on. We get this famous sequence 0, 1, 1, 2, 3, 5. The Lucas or Luca numbers, pronunciation depending on how sassy you feel, are a very similar set of numbers, except the 0th term is 2, so the sequence starts off with a 2 and a 1, 2 plus 1 is 3, 1 plus 3 is 4, and so on. Have a set of numbers, the Luca numbers, which follow this nice pattern, and what I was wondering was, can we find numbers which fill in the gaps? For example, what's between the third and the fourth Luca number? And it is possible to do this because there's a really nice formula for the nth Luca number, and I wanted to turn it into a continuous formula. And in fact, here it is. The nth Luca number is given by phi to the power of n plus minus 1 divided by phi, also to the power of n, where phi is this famous number in maths, the golden ratio. So at first it looks quite straightforward. I'm just going to make n continuous and bang, I'll get a set of numbers to fill out the Luca numbers. It's not so straightforward though, because if you think about, say, n equals a half, you have a negative number to the power of a half, or the square root of a negative number. That's going to give us an imaginary number. So that means we have to take things into the complex plane. So we want to turn this formula, modify it slightly, so it gives us a real part and an imaginary part, so we can plot in the complex plane. Let's go about doing that. So first off, a bit of tidying up. I'm going to call 1 divided by phi, phi to the power of minus 1, and that rolls over to minus phi to the power of minus n. Now that minus 1 is the part that causes problems. Let's take that out. Let's have minus 1 to the power of n multiplied by phi to the power of minus n. Good. And at this point, let's make a substitution. There's a really famous formula for minus 1, and it's this. Minus 1 is equal to e to the I pi. Wonderful formula. And if you haven't seen any complex numbers before, I really recommend doing a course on them. There's loads online. And we're going to use this substitution to give us a complex version of the formula. And you might note that because we're using exponentials, we're using minus 1 to the power of n, minus 1 to the power of n is going to be e to the I pi to the power of n. I can just multiply that n and we get e to the I times n pi. Really nice. So let's substitute that in, and we get the nth Luca number is equal to this expression, the golden ratio to the power of n plus the golden ratio to the power of minus n multiplied by this new factor, e to the I n pi. So already you see it's looking really interesting. We've managed to get pi into the Luca numbers. And I'm going to make one last substitution. E to the I n pi is the same as the cosine of n pi plus I times the sine of n pi. And that's all we need to do. So here's our final expression. The nth Luca number is given by the golden ratio to the power of n plus the cosine of n pi multiplied by the golden ratio to the power of minus n plus I sine n pi to the power of, times the golden ratio to the power of minus n. And that's the formula I'm going to use when I go to my spreadsheet. And I'll just note the first half there, that is real. So there's no i's over there. Those are all real numbers. So I'm going to plot those on the x-axis to make the complex plane diagram. The stuff with the I though, that sine m pi times the golden ratio to the power of minus n, is imaginary. There's an I there, so that's going to go on the y-axis. And before I show you the graph, just note there's a very similar formula, Binet's formula, for the Fibonacci numbers, so you can apply this to Fibonacci as well to see what the Fibonacci numbers look like in the complex plane. Right, now let's go over to the spreadsheet. I'll see you there. So this is the spreadsheet, and in column G here you can see I've just put the golden ratio for reference so I don't have to rewrite it each time I use it. I've put a variable called step, the idea being that I can choose which increments I go up to in finding the Luca numbers, and finally this one start, that's going to be the position, the value of n we start at. So I'm going to have n starting at 0 going up in steps at 1, as you can see over here in column A. That's quite straightforward. I'm starting at 0, so I'm using that G3 value. At each time I add the step, and I've put my formulae into columns B and C. We've got the real in column B, the imaginary in column C. And I've set the step to 1 so that we can just check, firstly, the real values are indeed the Luca numbers. Look, you can see that each number is the sum of the two preceding values. And the imaginary numbers are all very small, they're 0. Not exactly 0, but they're close enough for our purposes. That's good. And if you're wondering, that's how I entered the formula for the real part, shown in the box at the top now, and for the imaginary part there. And it would be really great if you could try this as well, so that you can investigate this sequence of numbers. Now let's do what we wanted to find. Let's change the step to 0.1, for example, so now we can see how the Luca numbers progress in between those integer values. And it looks quite interesting. I've got the graph ready. I'm trying to delay your gratification. Let me show it to you now. I'll bring the graph in, and we get this fantastic spiral starting at 2 as the 0th Luca number, goes back round to 1, and then up to 3, 4, and so on. I'll just point out that where we hit the x-axis, those are purely real numbers, no imaginary part, so that line gives us the Luca numbers, which we're familiar with, the 2, 1, 3, etc. But you can also see, when you look at the complex plane, you can see these wonderful details of first the spiraling and then the sort of wavy nature brought in by those sines and cosines in the formulae. And in fact, the Luca numbers are also quite spectacular if we go to negative numbers. Let me go to -2, for example. So we're starting at -2 here. We can see we have a nice backward spiral now. So we're starting off at 3, spiraling back to -1, and then we go to the 0th Luca number 2. We have this wonderful shape here. It's almost a Nautilus shell, which then turns into a nice sinusoidal sort of a curve. Wonderful. That's really interesting, but it doesn't have to end there, and I'm really hoping that you will try to build a spreadsheet like this as well, so you can investigate. There's all sorts of things to try out. One recommendation is try some other numbers in here. What would happen, predict what would happen if you set the constant, instead of the golden ratio, what happens if you set it to 1? What's that going to do? What happens if you set it to the silver ratio instead of the golden ratio? What about the plastic ratio? So do have a go and see if you can find anything else, any other interesting patterns using this formula. Also, of course, there's Binet's formula, as I mentioned. Look that up and try using that to plot the Fibonacci numbers in the complex plane. Thank you very much for watching. That's all from me. Thank you very much for watching, and I hope you've been inspired to fire up a spreadsheet program and have a go at this yourself. Thank you.